these graphs of modulation frequency of these micromechanical oscillators by utilizing the strong nonlinearity of the Casimir interaction and asymmetric structure near the exceptional point. It's possible to break the time reversal symmetry by modulating the separation between dual cantilevers, the micromechanical resonators, at the desired frequency and amplitude. So using this technique, researchers realized non-reciprocal energy transfer with the Casimir interaction. So this is one of those examples of, moving past is the idea of the quantum vacuum energy theoretical, or should we think of this as real or not? This is an example of understanding that it's very real, very substantive, and engineering devices based on that energy, that 0-point energy density of the vacuum. So we see this ubiquitous 0-point energy is not theoretical, but is observed in many natural systems, experiments, and even directly for technological application. And we are talking about a lot of potential energy. One reason why our research efforts here at the Resonance Science Foundation and with Nassim are focused on engineering methods that can harness the energy of the quantum vacuum, because there's a lot of potential energy there. Before renormalization, the vacuum energy density is calculated to be infinite. After renormalization, where you introduce a cutoff value, usually the Planck length cutoff value, so you can only have energetic oscillations, little quantum harmonic oscillators that are of the Planck length, nothing smaller. That's your cutoff value. When you do that renormalization process, then you get a finite number, and it's generally calculated to be about 10 to the 113 joules per meter cube. In a cubic meter, 10 to the 113 joules of energy. Now, I would be remiss if I didn't point out that that renormalization procedure is very arbitrary. I mean, there is some logic behind using the Planck length as a cutoff value for the size of your oscillatory modes of the vacuum energetic vacuum oscillations. But in the work we're doing, in the work Nassim has done, he's shown that undoubtedly there are sub-Planckian oscillators, sub-Planckian energy values. So really, the vacuum energy density probably is infinite. But we can take this number here. And so compared to the annual global energy consumption, I think one of the most recent values was estimated to be about 10 to the 20th joules for all of human civilization. So the amount of energy in a cubic meter of space could very easily satisfy the entire annual global energy requirement for human civilization. So just tapping that a fraction of the potential energy there could satisfy our energy requirements nearly indefinitely. And probably if we were to realize that kind of technological capability to harness the quantum vacuum energy, the ultimate source of energy, that would almost immediately elevate us to a type 1 or 2 civilization on the Kardashev scale. Right now, we're a type 0 civilization. So this will be one of the most significant and momentous discoveries and technological applications of human civilization. And I mean, it will totally change the course of human civilization because we will have a limitless clean source of energy. And we won't need hydrocarbon fuel sources. We won't even need solar energy sources, wind energy sources. If you can tap it directly from the quantum vacuum, that changes everything. And so it's actually something that is desperately needed and quickly. So this is very non-trivial considerations, non-trivial research. Now, as we were discussing a little bit, this QCD simulation is showing fluctuating gluons and quark gluon plasma. And this is how hadrons get 98, and actually, I think 99% of the mass. It's not attributed to the so-called Higgs mechanism. Now, what this means is that the strong force is the vacuum energy density. This is the same thing that Nassim points out in his paper, Quantum Gravity and the Holographic Mass. That the strong force, the nuclear confinement force, is the vacuum energy density. This is also what QCD is saying, except they have a little bit more how should I put this nicely, goofiness to it with the quark gluon plasma. Now, so your Planck density, so that's the 0-point energy density, the vacuum density, is what's producing the energy of the strong interaction. Now, in Nassim's work in quantum gravity and holographic mass, you get the exact value for the coupling constant between gravitation and confinement at the proton scale. That is the strong interaction but it's described in terms of a gravitational force, a strong gravity. So you've got your volume entropy R. That's your Planck density. That's the 0-point energy density of the vacuum. And it's calculated in terms of the quantum harmonic oscillators of the quantum vacuum. In this case, we're conceptualizing them as Planck spherical units. So little spherical oscillators, or you can even think of them as spherical vortexes. And this goes back to the insight that Ken pointed out, shared that there's a very definite structure here because these are overlapping, these little spherical oscillators of vortices are overlapping, so you get optimal packing in the volume of R here. Now, the holographic ratio between the surface entropy, the value of those Planck spherical units packed along the surface, overlapping along the surface. And so the holographic ratio between that and the volume entropy, and entropy in this case also means like information, like a Shannon entropy. That gives you this holographic ratio. This is a universal constant, phi here. With eta over R, you'll get the mass of any black hole. The reciprocal, R over eta, you'll get the mass of, at the hadron scale, the mass of a proton. And so we can see 2 phi times the Planck mass. So that's the Planck energy density here with this factor of 2, which shows up quite often in physics. We can take that and when we square these terms, we get 4 pi squared h bar times the speed of light over g, the gravitational constant. And when you calculate this, it's at 5.89 times 10 to the negative 39.